So in this particular video, there is the motion of a car moving along a straight line under constant acceleration, aka uniform acceleration, and the motion is shown in the position time graph on the right here on my screen. Okay, so here we have an xt graph that corresponds to the car's motion along a straight line, aka along the x-axis in this case. All right, so it asks us for all these different parts: A, B, C, D, E, F, and G. So let's take a second here to really understand what the heck is going on with this particular graph. Okay, so when you're given a graph representation, it's important to interpret information correctly. So the way I interpret this graph is that here the object starts at the origin because this is a position time graph. It starts at the origin and then it is going to move in the positive direction. Well, how do I know that? Because at 20 seconds it is at a position of 800. So it started from the origin on the number line, and 20 seconds later it is to the right of the origin, a distance of 800. So that would indicate that it's moving in the positive direction. And then at this peak here, it's important to find this critical point. This little dot here implies that the object's velocity is 0 at that moment in time. And then it stops and then it turns around and goes in the opposite direction. So this is what an upside down parabola tells you, that an object moves in one direction, it comes to a stop, and then it turns in the opposite direction. Okay, so that's important to keep that in mind as we proceed here. So object's going to move in the forward direction based on my cursor. At 20 seconds it comes to a stop because the tangent line here is flat, and if the tangent line is flat, it implies your instantaneous velocity is 0. But then what does it do after it stops? It actually turns around and goes in the opposite direction. So we have a negative slope here compared to a positive slope on the left side of the graph. So positive slope implies it's moving to the right, negative slope implies moving to the left, and then at 40 seconds, if you go all the way back to the vertical axis, it's back to 0. Okay, so let's do part A and B. All right, to do part A, it asks you to find the average velocity between 0 to 30 seconds. So as you practice, pay attention to intervals of time. Average velocity is displacement over time. I can pull out my displacement from this graph pretty quickly for the time interval given. One, I want to go from 0 to 20 seconds. I'm going to go from 0 to 20 seconds because I know that the object starts at 0 meters and then 20 seconds later it has traveled to the right a distance of 800 meters according to this graph. Okay, but I'm not done yet. It wants us to go from 0 to 30. Well, I just went from 0 to 20 seconds, and now I have to go from 20 to 30. But at between 20 and 30, it has traveled backward a distance of negative 200. So if you draw these vertical arrows up and down, it tells you how far the object has gone to the right or left. Okay, so the first 20 seconds, it traveled a distance of 800 to the right, and then between 20 and 30, it traveled leftward a distance of 200. But here I have it as negative 200 because it's displacement, which needs a direction. All right, other than that, the purple arrow that's going to come up here, that represents the change in position, which is from start to finish. The object starts at the origin, which is on the horizontal axis, and then 30 seconds later it ends on the graph right at about 600. Okay, so displacement is a straight line between start to finish. Therefore start is at 0 meters and then it finishes at 600, so therefore my displacement in this case would be a positive 600 because the arrow is pointing upward along the vertical axis. Okay, so and here's another representation for you if you need. So again, if you don't know how to interpret this graph, it's okay to draw a number line. Draw a number line, half the object starts at 0 because it says so in this graph, and then my arrow here, as you notice, is pointing to the right. Why? Because the object is moving in the positive direction and it stops at a position of 800. So here's 800, but then from 20 to 30 seconds it moved leftward a distance of 200. So I'm going to draw my arrow pointing to the left here for 200, and again you notice here is negative 200 because this displacement. So get used to distance and displacement and the differences between them. All right. If I were to draw a straight line from start to finish, which is what the purple arrow is representing, so if I just put a dot from start, I draw a straight line that connects start to finish. That displacement there is 600 to the right. Why is it to the right? Because the arrow is pointing to the right from where it started. So here I have it as plus 600 meters. Okay, so therefore we know our displacement is 600 meters, or plus 600 if you want. I don't really use the plus sign when I'm doing my calculation. I just kind of use common sense based on what needs to be at the very end. Therefore, 600 meters divided by 30 seconds is 20 meters per second. And here I've chosen to include the direction is east because the purple arrow ultimately is pointing to the right, which is east. Or you can simply put a plus sign in front of 20 meters per second. But it is a velocity, which is a vector, so you do need to include direction. So that's our answer. Let's do part B. Part B asks you to find the average speed during the same time interval. So it's important to know that because the object turns around after 20 seconds, but our time interval is between 0 to 30, which implies that the object is going to go 800 meters to the right, which took 20 seconds, but then from 20 seconds to 30 seconds, it travel in the negative direction. Okay, so to find average speed, we need total distance divided by total time. Here, I've chosen to write it as D1 and D2. D1 in this case would be the 800 meters to the right. So during the first 20 seconds, it covered a distance of 800 meters to the right. And then from 20 to 30 seconds, it covered a distance of 200 meters. And distance is a scalar, so you just add all of these lengths. 800 pointing upward, and then 200 pointing downward. Therefore, you have a total distance of 800 plus 200, which is 1,000, and then 1,000 meters divided by 30 seconds, which is 33.33 meters per second. Okay, so that's our answer for average speed. So you notice here these two values are not the same. Average velocity and average speed are only the same magnitude if and only if the object moves in one direction and never turn at all. But in this case, it does turn. Therefore, these values, as you can see, turn out to be different. So keep these concepts in mind as you practice. All right, let's do part C. Part C asks you to find the average velocity between 0 to 40. Well, to find the average velocity between 0 to 40, again, I'm just going to go ahead and use delta x over delta t, change in position over change in time. But this one is pretty straightforward. If you pay attention to the previous one, from 0 to 20, it traveled forward a distance of 800 meters. And then from 20 to 40, it traveled backward to where it started, which is leftward, the same distance, but just leftward. So visually, if you look at these two arrows, you're going to the right 800, but then you went left 800 all the way back. So you're at the same starting point. Okay, if you're at the same starting point, well, you haven't really displaced anywhere. So therefore, delta x is just 0. 0 divided by 40 seconds is just 0. So your average velocity in this case would simply be 0 meters per second. And because it is 0, you don't need to put a direction or anything like that. Now, if you had a hard time keeping up in terms of visualizing it with the graph, here, the arrow that just came up on this bottom on the right screen. So the object during the first 20 seconds moved 800 meters to the right. But then from 20 to 40 seconds, it moved the same distance but in the opposite direction. So this would be, same magnitude but just in the opposite direction. So that's 800 there, and then that's negative 800. So really, if you sum it up, 800 and negative 800, that'd be 0. Or you can just look at this arrow. You start here at this location where my cursor is tracing back and forth, and then you end up at the same position. So therefore, displacement must be 0. So our answer is simply going to be 0 meters per second. Okay. All right. Part D asks us to find the average acceleration. So let's knock this out. It says here in the wording that it experiences constant acceleration. So in this case, the object is moving to the right to begin with, and it starts to slow down. We know that it starts to slow down because the tangent line keeps getting more gradual, and then eventually it comes to a stop at 20 seconds, and then at 20 seconds it speeds up in the opposite direction. Okay, so therefore we can just apply average acceleration is equal to change in velocity over change in time. We can break up delta v into vf minus vi, and really we just kind of assess what we know and we don't know. Here you have to be really clever. It asks for average acceleration, and it didn't really tell you exactly how to do so. What I've chosen to do is I've chosen to start from 0 seconds to 20 seconds. Now, why would I go from 0 to 20? I want to go from 0 to second to 20 seconds because at 20 seconds, I know my velocity, my instantaneous velocity is 0. Because if you draw a tangent line, at 20, that value will be 0 because the tangent line is just straight horizontal. And if it's a horizontal line, the slope is 0. The slope would suggest that the instantaneous velocity is 0. Alright, so here I have Vf as 0 for that reason, because I've chosen to go from 0 to 20. My Vi, I don't know what it is. So it's important not to assume that Vi is 0, because the tangent line at the start of the graph is a steep tangent line, which implies that Vi is not 0. It's a common mistake that kids might look at this and say, well, the initial velocity is 0. And I would say, no, it's not. This is a position versus time graph. The object starts at an initial position of 0 meters, but it's already moving. How do I know that? Just draw a tangent line. The tangent line is not flat, so therefore the object is already in motion. You might not know what it is, but it's definitely not 0. Okay, so here I've chosen to go from 0 to 20, so Vf here is 0 because, again, that peak tells me V comes to a stop. I don't know what Vi is because the graph doesn't give it to me directly. And here my delta t is 20 seconds because I've chosen to go from 0 to 20. Well, the only thing that's really missing here is Vi, but that's okay. So as you do these ones, these position time graph, you just kind of learn how to be more clever, which time interval to look at in order to find what you're missing as quick as possible. Here, I've chosen to set up the two average velocity functions under constant acceleration. Delta x over delta t equals Vf plus Vi divided by 2. Well, I know what delta x is if I'm going from 0 to 20 seconds. My delta x is simply 800 meters because that's what the graph shows. Okay, therefore I can just do this. You notice here on the graph here, I just drew a tangent line. I don't know what that is, but I know that's Vi. Well, how do I know it's Vi? Because at times equal to 0, the object's already moving. So that's my initial velocity. So I don't know what the steepness of the tangent line is, so I don't know what Vi is. All I know is that Vi is not 0. So don't make an assumption that's false, because once you make the false assumption, all your work is going to be wrong. Okay. At the very top of the peak, you notice I draw a tangent line. A tangent line touches a single point on the curve. Well, if you draw a tangent line at the peak, it is going to be a straight flat line. Well, if it's a straight flat line, it implies that the velocity at 20 seconds is 0, aka V final at 20 seconds is 0 meters per second. And that's important because we can use this information to find Vi. Here, delta x I substitute for 800 because from 0 to 20 seconds, if you just take your pencil, you go from 0 second to 20, and you go all the way up to where it touches the graph. That is a vertical distance of 800 meters. Okay, going up and down is really going right and left. All right, and then over change in time is 20 seconds. Vf is 0. Vi, I don't know what that is. As a matter of fact, that's what I'm trying to figure out, because on the left side of the average acceleration equation, I'm missing Vi, and that's the unknown in my function. So here, using this work, I can find Vi. To find Vi, you simply get rid of the 2 denominator by multiplying both sides by 2. And then that's it. Okay, so multiply both sides by 2 and you'll get this. And if you simplify that on your calculator, you should get a value of 80 meters per second. So my Vi here is 80 meters per second, and I know it's positive because the slope here at the very beginning is a positive slope. So I can say Vi is positive 80 meters per second. But I'll leave the sign out when I'm doing my work. So once I know that Vi is 80, I can plug it in for Vi in the average acceleration equation. And once I do that, it really looks like this. A average is equal to 0 minus 80. The negative sign is part of the equation. And if you carry that negative sign down, it will be negative 80 divided by 20 seconds, which is a negative 4 meters per second squared. And the negative sign here fits with what it's doing. Here in this graph, we know the velocity is the tangent line, but the tangent line is positive. And if the V is positive for an object to slow down, acceleration must be in the opposite direction, which is negative in this case. So therefore, A average is negative 4 meters per second square, which makes sense to me. Okay. All right. So that's part D. Now, that's a lot of work. Okay. By the way, I do want to point out that in doing this strategy to find A, you actually found the answer to part E as well. So I do want to point this out before I forget. The answer to part E, this is the initial velocity at t is equal to 0. Well, the proper answer would be Vi is plus 80 meters per second, or 80 meters per second east. So sometime coincidence happens, in doing certain strategies, you actually find the answer to different parts of the question. So the answer to part E is simply plus 80 meters per second, because I just found it here by needing it for the average acceleration equation. The other part, the other strategy to find part D, to find the average acceleration, which I like a lot. So hopefully if you listen well, you'll like it too. You just have to learn how to read these graphs, okay? You don't have to always start from the left side of the graph and then go to the right. You can start at any point on the graph as long as your facts are true. So here I have my displacement function. Delta x is equal to vit plus 1/2 at squared. I'm trying to find a. Again, part D is asking you to find a. So I know my vi is 0 if I start from, ready, 20 seconds and go to 40 seconds. Okay, this is important. In order to find a using this strategy, I'm actually going to start at 20 seconds and go all the way to 40 seconds. Now, why would I want to start at 20 seconds? Well, I want to start at 20 seconds because I know that the final velocity on the way up here is now 0, which becomes my initial velocity on the way back. Okay, so here vi is 80 and then it approaches vf, which is 0, but the vf now in the second segment is my initial. So if I start at the peak, I'm starting at rest. Well, if I start at rest, my vit term cancels out, and really it makes the whole problem easy to solve. Here I've chosen to replace my delta x with negative 800, because if I start at 20, I want to go all the way to 42nd, and you see my cursor is moving downward. Well, how far did it move down? Negative 800. Okay, just the same length, just in the opposite direction. 1/2 is part of the function. A, I don't know what it is. My t here is 20 seconds, and then the square is part of the function. It's 20 seconds as I have chosen to start my problem from 20 seconds to 40 seconds. And this is a trick that a lot of kids don't see, which I hope you do see. Okay, so if you do that, you can just solve for a by simply multiplying both sides by 2 and then dividing 20 square, which is 400 on the bottom here. And if you do that in your calculator, you'll get the same answer of negative 4 meters per second. So I like this strategy a lot because I can cancel out VI. I can cancel VI because I know that if I just reverse the situation, the car starts at rest. Okay, think about it. If it makes sense, use it. If not, hopefully go with the left strategy. It's just a little more work. All right, so let's do let's do E and F. Okay, let's do F and G. Part F asks you to find the instantaneous velocity at 12 seconds. Well, it's just asks you to find VF, so let's just knock this out really fast. V of t, here I've chosen to write this notation V of t. You can just write VF if you like, which is AT plus VI. We know what A is. A is negative 4 meters per second squared for the whole entire problem. Well, how much time? Well, 12 seconds. I've chosen to go use 12 seconds because I want to start my problem from time equal to 0. But if I choose to start my problem from time equal to 0, my initial velocity, which I found in the previous part at time equal to 0, which is 80 meters per second. So if you simplify it on your calculator, you should get a value of 32 meters per second. And then make sure to include the direction because instantaneous velocity is a vector. So make sure you either put plus 32 meters per second or comma east. Okay, so that's part F. And then by the way, make sure you check your answers to see that it's reasonable. So here on the graph, this is a velocity versus time graph. So the tangent line to start was a positive 80, and then at 10 seconds, or excuse me, about 12 seconds, if we go up a little bit, yeah, you notice that the tangent line got more gradual. So the answer of 32 is less than 80, which is reasonable. You know, so if you get an answer that's like bigger than 80, you definitely should be checking the answer because that wouldn't make any sense. Okay, so here my answer falls between 80 and 0 because it comes to a stop during a time of 12 seconds, which is between 0 to 20. 0 to 20, so I know that is a reasonable answer. All right, let's do part G. To do part G, it asks us to find the average velocity between 10 to 35 seconds, which is a little different, but it's not that bad. So I'll do this function. Average velocity is VF plus VI divided by 2. The only hard part is really finding your VI at 30 and then finding your finding your VI at 10 seconds and then finding your VF at 35 seconds. So I'm just going to use this particular strategy from 0 to 10 seconds. I can just use my VF function VF is just AT plus VI. A is -4. Change in time is 10 seconds because I've chosen here to go from 0 to 10 seconds. And then my initial velocity that was calculated in the earlier part is 80 meters per second. If you simplify this in your calculator, you should get a value of 40 meters per second. And then so I know how fast it's moving at 10 seconds. Well, but I need to know how fast it's moving at 35 seconds, okay? Because I need two velocity points. Well, so we can just go from 0 to 35, do the same thing, from 0 to 35, A is still -4 meters per second square. Here my time though is 35 seconds because I've chosen to go from 0 to 35. But if I choose to start my work from 0 second, I need to plug in the proper initial velocity. So the initial velocity is 80 meters per second when time is equal to 0. So don't forget, the object is already moving, the car is already moving by the time this observation is made. So if you simplify this on your calculator work, you get -60 meters per second. Yeah. So we have our two values. But what I do like to point out is that in order to find the velocity at 35 seconds, there's a different way. I like the second way a little better because it's just a little less work. As a matter of fact, I can actually find the velocity at 35 seconds simply starting at 20 and going to 35. Now again, if you're sitting there going, well, why are you starting at 20 and going to 35? I'm starting at 20 seconds because at 20 seconds, I know the object came to a stop. So therefore my VI is 0, okay? Because 35 seconds falls on the right side of this parabola. So I can start at 20. If I start at 20, my VI is 0. So that's just one less term for me to punch in my calculator. So I hope you like this strategy. So the velocity at 35 seconds can also be calculated by A delta T. But you notice here my delta T is a little different because I've chosen to start at 20 seconds. From 20 to 35 is a difference of 15 seconds. So be careful with your time. And then plus 0. Why 0? Because my VI at 20 seconds is 0. The tangent line is flat, so it came to a stop at that point, then it starts to go around. Okay, so if you simplify this on your calculator, you should also get a value of -60. So here there's two different strategies to find velocity at 35 seconds. But now that we know the velocity at 10 and the velocity at 30, regardless of which strategy you use, let's just plug it in. VF is -60, VI is 40, and then add those two, -60 plus 40, that's -20, and then -20 divided by 2, which is -10 meters per second. And the negative sign is your direction, which is leftward in this case. All right, and the other way to do part G is to use the average, velocity function, which is displacement over time. And then from here, we know that the delta time or change in time is 25 seconds because T here starts at 10 and it goes to 35 seconds. So the difference here is 25 seconds. I don't know what my displacement is though. That's okay. If you don't know what your displacement is, just go find it. Well, delta x is VIT plus 1/2 AT squared. Okay, but here the problem starts at 10 seconds. Well, if you kept up with my previous work, you can find the velocity at 10 seconds pretty quickly by using the final velocity function. So here for VI, I've chosen to plug in 40 meters, not 80, not 0, but 40 because at 10 seconds, the car is already moving at a rate of 40 meters per second. Here my delta T is 25 because from 10 to 35 is 25 seconds. A is -4, and then my time here is 25. I'm going to square that. So if you simplify all this in your calculator, you should get 1,000 meters plus -1,250 meters. That reduces down to -250 meters. Well, now that we know what our displacement is, which is -250 meters, it's super easy to do. Just plug it back into the original function, which was you're missing. But what I like to point out here is this. You can do all this calculator work, or you can just kind of reason things out using a graph, especially when things are nice for you. Here, I've drawn two horizontal lines. Now, why would I do that? Well, I can find the displacement between from 10 to 35 seconds. So watch my cursor. From 0 to 10, I want to go up, and the object is at a position of 600. That's where this is, 600. But then if I keep following the graph, or if I go back to where my horizontal time axis here, if I go all the way to 35, and 35 is right here, it kind of intersects here on this graph. Therefore, I just drew two horizontal lines, so I can find this distance here. So you notice here this arrow is pointing downward because at 10 seconds, the object is at a position of 600. It kind of follows this curve all the way around, but then by the time it gets to 35 seconds, it's beneath 600, which means that the displacement is negative. Okay, so if you kind of think about it, it starts at 600, and then at 35 seconds, if you kind of eyeball it, you go to the left here. This here is about 350 because that's about midpoint. So from 600 to 350 is a difference of 250. Now, why is negative? Because you went from 600 to 350 on the number line, which implies that you're moving leftward. So therefore, that's negative 250. But once you find out the delta x using math, which is negative 250, you can just plug in for delta x here. And then delta x here is negative 250 divided by 25 seconds, which gives you the same answer of negative 10 meters per second. Okay, so again, there are different strategies in terms of how to solve these problems. I hope as you practice, you learn how to extract information from an XT graph correctly, and it just helps you knock all these different parts regardless of what I ask of you. All right, stay nerdy, don't be whack.